properties are going to relate. So you formulate, you cook it up, and then you say this is the formation it should be, and from there on you can pick it up, right? It may not, for undergrads this is not going to work out. But I'm talking about, when you're a researcher and when you're, thinking beyond what the textbook teaches you, right? So that's what we do. I mean, as you mentioned earlier, and also I mentioned that this photonic integrated circuits, or these topics are a little advanced, right? It's not, there in the textbook that you go through, read, and then you get it.
Excuse me, sir. This is Naveen.
Yeah.
Yes, sir. We can start, sir. We are live. We are in live in YouTube.
Good. All right. Welcome, everyone. So this is our final, live interaction. So before you take the exam, end of this month, I think, right? So there was some email on some dates for some states and so on, but nonetheless, it's going to happen, and NPTEL Central Nodal Office will take care of timeline and so on. So the idea here is to, just listen to you guys and about the preparation for final, exam. If you are planning to, of course, like, I know that most of the folks, they just take it, learn it, and there is no need for, don't see need to take up the test or certificate exam. That's also, fine. But as long as you go through this exercise, of learning and understanding, that's good.
Good afternoon, sir.
Yeah, good afternoon.
This is Akhil, sir.
Yeah, Akhil, sir.
It is very glad to talk with you, sir.
Yeah, likewise. I saw you. Nice. Thanks for, showing interest in the course and learning.
Yeah, amazed with this, sir.
Yes.
I'm really amazed with this type of opportunities, sir, from NPTEL courses.
Good. See, that's the beauty of NPTEL.
Okay, sir. Photonics is too virtual, sir. It is very, very difficult to imagine what the actual thing is, sir.
Correct. See, unfortunately,
Sir?
Photonics is nobody's child, you see. So when you look at physics, right, you have physics folks, they will talk about optics and so on, right?
Yes, sir.
And then you have engineering people who will talk about using light, right? Optical communication is one area that you do. But then if you look at photonics as such, if you go to someone who is doing physics and you talk about applied things like photonic circuits and so on, they will say, no, this is engineering. This is not physics. Then if you go to an engineering guy and said photonics is interesting, you can do all this. Oh no, it's too physicsy. I don't think I have the background to do that. So because of this, unfortunately, our curriculum has failed to address this gap. We could have done better. So we would like to see how one can improve the scenario and then photonics to a new level in the country. So people like you, if you are interested now, probably will take up photonics as one of the areas to work in going forward. So that will be, really amazing thing. Okay. There is something from Harsh message here. This is from Harsh. Say now. I'll deal with the layers during fabrication of. Okay, let me. So everyone can read the question, or no? You cannot read the question. Let me read this question. The question is about fabrication, right? while we deal with layers during fabrication of near micro nanometers in different processes, how the precision and accuracy is maintained in this chemically layers, okay? Removal addition process. Could small errors in manufacturing go very wrong in functioning of final product? Yeah, that's a good question. So the question is there for everyone. Good. Thanks, Naveen. So the question is about, when you are, we looked at the photonic circuit, right? So we have multiple layers, and the layer thickness was not too much. So we talked about 220 nanometer, 200 nanometer, and so on. And the line width, right? So the width of the waveguides are not also reasonably small, right? So they are narrow lines, 400, 500, and the max a micron or so, right? So the question here is, how do we precisely control the thickness? One, and then whether there is a change in the dimension or thickness will have an effect. And how about the chemical nature of this surfaces, right? Because we say it's silicon or silicon dioxide or silicon nitride, silicon carbide, you take any material, or indium phosphide, all these compound semiconductors. So what happens when it is, chemically affected and so on, right? So let me answer this question one by one, right? The first thing is the dimension, right? So the thickness, how do we control the thickness, right? So the thickness is controlled by the fabrication process itself. So we use deposition techniques. And if I ask for 200 nanometer, right, you may not get 200 nanometer. You will get, 200 plus or minus, let's say 10 nanometers, right? The worst case scenario. So you will have 190 nanometer and then 210 nanometers. So that is the thickness variation that you have. This is true for any kind of fabrication, right? When you take any objects that you fabricate using, lathe, for example, right? In a mechanical lathe, or even carpentry, you always measure and do it, but there is always a delta, right? And this delta will be there. It is there when you go for any practical equipments. You will have these kind of changes, right, in the dimension and so on, and one has to accept that. Okay, and when you are designing your device, you have to take care of this variation. So when you design a device, you do this simulation within this window. You say, okay, if my thickness goes from 190 nanometer to 210 nanometer, whether my response is going to be within my acceptable limits. Okay, the same thing is true for line width as well, right? I ask for 500 nanometer line, and this could have 10% variation. So there again, one should design, these devices that could be, tolerant to this, what we call fabrication imperfections. So the bottom line here is, change in dimension will result in change in response, right? What kind of response? It will be a spectral response, right? So the degree of this change, I think we have discussed in the lecture. I think if not, I will repeat it. The thumb rule is, this variation strongly depends on the type of index contrast you have, right, between the core and the cladding. So the higher the refractive index contrast, the higher the lower the tolerance, right? For example, optical fibers, the tolerance is very high because the contrast between the core and the cladding is very low. But if you take silicon waveguide surrounded by oxide, silicon dioxide, there the refractive index contrast is very high, right? Silicon is 3.5 and oxide is 1.5, right? So this contrast gives you very large difference and highly tolerant, highly intolerant to size variation. So what is the magnitude of this size variation? Right. The thumb rule is, at least in high index contrast platforms like silicon, 1 nanometer change in the line width, right, or waveguide width or height will result in 1 nanometer shift in the spectral response. That is quite a lot, right? So if you look at communication, right, optical communication, for example, 2 channels are spaced, 50 gigahertz apart, right? 50 gigahertz in 1550 range is about 0.4 nanometers. There are 2 channels, right? Channel 1 and channel 2. So these are all only 0.4 nanometer apart, right? 2 data channels. And now if I tell you that 1 nanometer change is going to result in 1 nanometer change in the spectral response, right? For example, I have a filter for these 2 channels, right? If there is a change in the fabrication, then I won't be able to have a device that can discriminate these 2 wavelengths. All right? So that is a big problem, and that is one of the reasons why we need very high resolution patterning process and also robust devices, right, in order to make these photonic devices work for our specific requirement. And this is very intrinsic to guided wave optics. They are because you are interacting with the light in a very small volume. So each and every mono layer of interface, right, light will interact with those layers. Okay, so that is one part, right? And how about the chemical nature, right? So chemical nature of the light of the surface of this waveguides or the material could have an influence on the light propagation, and it depends on the nature of this chemical, right? Whether the chemical that you have, right, on the surface or even within the material, whether this material absorbs light or not. If the absorption coefficient of this particular chemical is 0, let's say, then you will not see any influence of this chemical change in the waveguide. However, if you have this material having non-zero extinction, right, the alpha is not 0, then there will be absorption loss because of this chemical. And we call this as contamination. When we are fabricating these devices in this big vacuum chambers, maybe someone has processed some other material, for example, right? And when you are doing your processing, there could be some cross contamination. So the products from some other material, some other sample can come and sit on your sample, right? So that contamination could result in these kind of absorption loss, right? And even metal contamination. So this is something I have also discussed in the course, right? These contaminations could result in absorption loss, not so much on the spectral characteristics, right? So they are very sensitive. And this is one of the reasons why we use these photonic devices a lot for sensing, because they are highly sensitive to their environment. So we could use these photonic devices as a highly sensitive optical sensors, because you have very huge light matter interaction. Okay, so I hope that clears all the doubt for that first question.
Yes, sir. Thank you so much, sir.
Thank you. All right. In terms of power consumption, do you think requires more power than a typical CMOS circuit? When we talk about optical communication, we use lasers. Can low power PIC come to market in smartphones? Interesting. So power is a big thing, right? So whenever we talk about moving data from point A to point B, one of the important metric is energy per bit, right? How much energy I spend moving from point A to point B, right? So just to give you an idea, in microelectronics, right? Even without moving, if you want to just look at the bit, right, in the memory, just go and look at whether that bit is 1 or 0. If you just want to touch the bit, you will already spend femtojoule for that. Okay, so you just need to, you're not doing any processing, you're just going and checking that. Now the question is, if you want to communicate that, whether optically doing that is beneficial compared to electrical, right? And there are two scenarios. One is point A and B, whether these point A and B are very close to each other, perhaps centimeter scale, or whether these 2 points are kilometer apart, right? So we already know these 2 points that are kilometer apart. Electrically, it's not possible to have an efficient transmission. That problem is solved. Now the question is, how about shorter distance? Can we do even better? So that is where we need to look at the loss component, right? Where does electrical power requirement clearly goes beyond acceptable limits, right? And that limit is dictated by the speed of operation. For example, if I want to move data in megahertz, right, then, or megabits per second, that means, right, or even gigabits per second, right, a single chunk, or aggregate data rates of gigabits per second, then I can still do that, okay, because the loss that I have is manageable. I don't have problem with the loss. But then if I go to tens and hundreds of gigabits per second, that is when the problems comes in, because you will have huge radiation loss, right? So that is the frequency of data transmission increases, and that will increase your power loss. So we know our power loss is directly proportional to frequency squared, right? So when you increase the frequency, the power law shoots up, and that is the point you take a decision that, okay, it's not sustainable to do electrical communication. We can move into optical. So let's look at again optical, whether optical will be better than that, right? So now we say we can take a call that, okay, this is going too much, but we need to find an alternative. Whether optical communication is the alternative or not is the question, right? So the decision only comes in when you cross that limit where the optical power consumption, right, is lower than the electrical loss. The reason for this is optical communication is not cheap when it comes to power budget. When I say cheap, not cost, but power wise, right? We need to put in enough power to generate light, right? So light is generated by this very small, diodes that requires milliamps of current, and that also dissipates a lot of, power, right? Sometimes milliwatts to watt level, right? Depends on the distance that you want to communicate and so on. You can have milliwatts level, but the heat dissipation is also an added factor, right? So whether you have reached a frequency level that you can tolerate optical, right? So that is the decision point where everything will transition to optical, right? That two scenarios. One is the power loss is too high and signal integrity is very poor, and the second point is you won't be able to transmit at this speed at all, right? Because you do have cutoff for your copper lines, right? So we use copper lines, so you do have a frequency cutoff for copper, right? That's why we use very thick copper for high frequency communication, right? RF, high frequency. When I say communication, it's RF. We use thick copper cables to reduce this loss. But we cannot do that at chip scale, right? We cannot make very thick wires, right? So that is the point where we will take a decision that there are no other solutions other than to go for optical. All right. So that is the decision taking point, right? Where to do this transition. And the other question is, can we use this in smartphones? Absolutely, we can do that, right? There are a lot of efforts now to integrate this, photonics-based approach for different application, not necessarily for communication, but there is a lot of application in sensing, right? That people are using, and also imaging type applications, where PIC will have a better chance than the electrical counterparts. All right, so that is one thing. Why should we wavelength filter while color is frequency dependent? Okay. I'm trying to understand what you mean by why should we filter the wavelength instead of colors. Okay. So we don't, the color is, something that only exists in the visible range, right? If you go beyond that, there is no color. At least for us, right? There are different species with different, visual colors and so on, right? So color is not really a physical quantity. We just give it because we see it in visible range. While wavelength is something that you can measure, right? That depends on the material and so on. You can actually interchange frequency with wavelength because it depends on where you come from. If you are coming from communication side, normally people use frequency. They will always talk about terahertz, this 193 terahertz, 160 terahertz. So those are all optical frequencies. It's still okay. You can design everything in frequency domain. That still people do that. Some of the simulation tools actually does this, right? So they do all in frequency domain. But we don't use colors, right? So color is not real. It's only exists in the visible range. Beyond that, it has no meaning, right? So we don't use color for that. So we can use frequency scale, or we can use wavelength scale. Okay, good. And the next question is from Jihan. Could PIC and spintronics be interactable? Can light change the spin of quantum number? Well, yes, you can. We have this ion traps, right? So the ion-based quantum computers, you can probe the ion state by using light. People have shown that, right? And the question here is, can I change the spin? So can I code and decode, right? It is certainly possible to do it. Light-induced, you need to design. You cannot do it for any kind of trap. We need to design a system that would respond to light pulses, right? And you can make it control and also probe pulse, right? So one can control the spin, the other can actually probe the state. So one can design it. The short answer to that is yes, you can do that. And people have shown probing. I'm sure that the controlling thing is coming, right? It's once you can read, you can also change the state. It's just a matter of creating an environment that will influence the qubit. Yeah, so this is an interesting thing. Okay, if we are going to use photonic ICs and spintronics together, how are we going to confine light? All right. So interesting question, but we all know about cavities. very small cavity volumes one could create, right? And these cavity volumes are reasonably small, right? So you can make large number of these cavities, particularly either one-dimensional cavities or two-dimensional cavities, right? So you can put these optical cavities, and also you can put your spins in these cavities. So a lot of engineering and crosstalk between these two fields should happen, but it's certainly possible. So that is how they do it. You create a cavity and then you put that spin in that optical cavity. All right, so there are a few more people who have joined. Welcome to them. So if you have any questions about the course or in general, or about the exam and everything, you can always ask me. Oh, Akhil, there is no difference between frequency and wavelength, right? So these are all two quantities that characterizes light. All right. So when you see any photon, the photon will have a certain frequency and a certain wavelength in the medium. So when you are filtering, it's not filtering frequency and not wavelength. All right. So when you filter a certain photon, you are filtering a certain frequency and certain wavelength. So it is related to that photon. So you cannot, just filter out frequency of a photon and not the wavelength, right? So these are all related, right? This is a characteristic of a photon. All you can do is filter a photon. That's all you can do. All right,
Sir, but frequency is time dependent and wavelength is space dependent, sir.
exactly.
How can these two are equal?
So when you say frequency, right, this is the nature of this photon. It's not going to change from material to material, right? So
Yes, sir.
for example, I say 150 nanometer light source, right? I want to filter this.
Okay,
So
sir.
what I mean by that is 1550 nanometer in free space. Okay, but then when it is goes through the medium, right, then it will be 1550 divided by the refractive index of that medium. All right, but the frequency of this light remains the same. So when I filter this 1550 nanometer in the circuit, what I'm doing is I am filtering out this 1550 nanometer. At the same time, that photon, right, that is carrying it, I'm also filtering it. All right, so you are right that wavelength is a property of light that depends on the medium, right? And frequency depends on time. And that is the reason why, frequency based design is much more, easily understandable compared to wavelength. But it depends on where you come from. As I mentioned, you can do both. All right. So all you are doing is the characteristic of this photon. You want to filter out a certain photon of certain energy. Wavelength is something that we use because it is, material. Because you when you are going to build a device, right, you have to talk about how the light is going to interact with this particular material, right? So that's the reason why wavelength is always important to mention here, because it is interacting with this medium. If it is in free space, we don't have to talk about this wavelength at all, right? You just take frequency, and wavelength of light is wavelength in free space. But then it interacts with this material, right? So that's where this wavelength factor comes in. These are all two different fundamental, quantities, but of a single photon.
Okay, sir.
All right. So there is one more question. Okay. Good. So I mentioned about this sensing, right? The question from Jihan here is that, this optical biosensing, why it is not widespread, right? The industry. So the pulse oximeter that you measure, right? That has LED that interacts with your body. Apart from that, there is none. So that's what this question is. The example is the PCR test, right, which takes hours. Why can't we do it faster and quicker? A simple answer to that question is yes. This optical biosensing, right, is something that is slowly and consistently evolving. The reason why this optical mode of sensing has not seen widespread acceptance, let's say, is the technology itself, right? This technology is highly sophisticated, right? And people who started doing this in the earlier time, the light that is required, the laser light that is required, the alignment of this light and so on was a huge problem, right? When you're building these kind of field application, right? So in field application, you are going to give it to a healthcare worker. He is not going to align things. He just wants to put the analyte, and then he wants to press button, and then it should give you answers, right? So traditionally, this optical instrumentation required all these alignment requirements, right? So that was the main reason why this optical sensing was confined to laboratories. In laboratories, we still use this highly sophisticated optical instruments, not in the field, right? Advanced microscopy, we still use it, right? But not in the field, right? So now things are changing. The reason for that is the advancement of micro and nano fabrication and texturing, right? Where we could confine the light in thin slabs, right? We don't need precise alignment. Based on those new technology, now the sensing modalities are also changing. Okay, so it's slowly coming in. And my positive outlook is that this is going to take at least next 5 years or so to slowly go into the field, right? Because it takes a time for people to accept the technology. It's not just the technology itself. It's about the acceptance of the technology on the field, right? It might be the best technology that you have, but whether the technology can be handled by someone, at the primary healthcare level. Okay, so the technology is slowly moving towards that. And the other important question that you raised is about this PCR tests and so on. So why can't we do it optically? It is done optically. I know two of my ex-colleagues. They have startups in one is a startup, the other one is much more matured in the US. They are doing COVID-19 detection using photonic ICs. Okay, so one is located on the East Coast, Boston. The other one is in California. So they do use photonic ICs for detecting COVID actually. So it is possible. Okay, it's about the sophistication of the technology itself. Okay. Things are hard to maintain. Yeah, I'm not sure what you mean by maintain here, Harsh, but could you just elaborate what you mean by
No, maintain. I mean by maintain that someone needs to be supervised over the complicated systems, right? As you said, in healthcare, a simple healthcare worker cannot operate such complicated.
I see. Yeah. So that the big technology itself, normally what happens is when you put out this technology out in the field, you don't expect those healthcare workers to understand and know about this PIC at all, right? So you have to do wrap around this PIC, right? So how it measures, what it displays, and so on. So that is all taken care, right? So one should take care of it. Otherwise, you don't expect PhD students doing all these tests, right? So you have to make sure that you take care of how the data is collected and how it is presented. So once you take care of that, then this part is actually taken care. Even electronic sensing, right? It is not straightforward because we have startups from Sense here at IISc that does biosensing and also gas sensing and so on. This is all at chip scale. But then there is associated data acquisition electronics, data processing electronics that will convert the current or voltage or capacitance that you are measuring into the concentration of gas, right, or concentration of a certain chemical and so on. So that translation one should do. Without that, it's a non-starter. Yeah, that's a good point. You should make the technology really accessible, right? You add these layers so that one can do that point. How can we do programmable PIC or reconfigurable PIC? Well, we have studied in the course. Programmable ICs are nothing but change the response of any device, right? For example, a typical device that we use for programmable ICs, particularly in photonic ICs, is a directional coupler, right? So you remember we studied about directional couplers, right? There are two waveguides and how you transfer light from one waveguide to the other, right? So you can control this transfer. And that's actually programming. How do you control? Either you create a micro heater, you put a heater in this particular region, or you can use liquid crystals to change the environment. So you change this environment of this directional coupler, right? And you can control the light flow either pass or cross, right? And you build a network of this. And that becomes a programmable IC. So you control, these are all nothing but gates. You're controlling the flow of light, right? So you can cascade number of these directional couplers, right? And then you can make the light go through the route that you want by controlling the directional coupler. So this is nothing but programmable ICs, right? Or reconfigurable. So this is something that one can easily do. But the important thing here is, I mentioned that it is not a single device. You see, we only studied one directional coupler. You should have hundreds or thousands of these couplers to make these arrays, right? So that you can create a functionality. The same thing like, field programmable gate arrays, FPGAs, right? You must have heard about FPGAs, right? So FPGAs are nothing but the same concept. You have, millions of gates, and you have to connect those gates in a certain fashion in order to realize a functionality. So the same thing we do here.
Sir. Sir? Sir?
Yes, Akhil.
Does light intensity decrease after polarization, sir?
Light intensity decrease
after polarization?
After polarization, yeah. It depends on what kind of polarization you are doing, right? For example, if you're doing polarization filtering, right? So I can have unpolarized light, right? I have all over the place. The electric field is all over the place. And then I put a filter, right? I put a filter, and then what I get is a polarized light, right? But then I will lose the rest of the light, right? I will only get this only one polarization here, right? So when you do such kind of polarization filter, then your power will reduce. Okay. On the other hand, I can take a circularly polarized light or a linearly polarized light and then pass it through a nonlinear crystal. We have seen this in our polarization, right? So when you pass this through a nonlinear crystal or anisotropic crystal, not nonlinear, I should correct myself. It's a anisotropic crystal. In that case, the power, the polarization will be rotated, right? You go from linearly polarized to circularly polarized to linearly polarized based on the angle, right? So in those cases, you will not lose power because you are merely rotating the electric field. However, when you do a filter, when you do polarization filtering, then your power will reduce. Okay, so these are the two scenarios. Okay. Would it be possible for me to make DIY project photonic devices? Things like laser pointers you get in stores and maybe 3D printers. Well, it depends on what you want. There are a lot of DIY stuff you can do, right? You know, if you tell me what you want to do, then you put all these components together. Okay, these are all the components that we need to put together to realize. For example, you can make your own projector, right? You don't have to spend so much. You can make your own projector, so that's something that you can do. And you can actually make a photonic, let's say, waveguide. You can make a waveguide on your own. That's also possible. You can do small experiments with it, but then it's going to be involved. It will not, going to be of any useful purpose, right? But you will see light going through the waveguide, and you can split light and so on. So those are all the things that you can experiment, right? Okay, so there is a question on the, Neetu is asking questions. I missed one of the questions earlier. So laser-based DPI test is currently used in UAE. What is that DPI, Neetu? I don't know what this DPI is. Or maybe there are a lot of other expansion for DPI. What is this DPI? I don't know. We'll move to the next question from me. Differentiation is interferometer, guys. Okay. I don't know what they use it for, but yes. The other question from me to the next to that, should you expect essay type questions? There are no essay type questions. Okay, so you don't have to worry about it. We have a multi-choice and then numerical. All right, so it's similar to the assignments only. Okay, so make sure that you go through all the assignments carefully. I'm repeating myself. Go through your assignments carefully, right? Repeat it, and then you should be able to easily get through the final exam. All right. So I have deliberately kept it very simple. Okay. Don't need to panic. Just go through your assignments. That should help you. Assignment solutions. I thought assignment solutions were already posted. If not, I will ask my students to post it. Yeah, the assignment solutions are there with us. I will probably try to post it or share it like we did for the notes. Will that be okay? So we'll just share the answers through Google Drive. That should be useful. Okay. Any importance for meta surfaces in PIC? Yeah, meta surfaces and PIC are slightly different, way of handling light. PIC handles propagation along the thin surface. So the light propagation is in plane, right? In meta surface, the light propagation is normal. So you do processing of light that is impinging normal or at certain angle, not in plane. So that's kind of meta surfaces do. But you can actually create some resonances, in plane resonances using meta surfaces, right? Actually, I was just reading meta surfaces. I mean, in this, just before this class, this came out in SPIE, right? So this is meta surface in that. So it's quite interesting because you can make all kind of lenses that this interesting insects they got, right? The compound eye that they have, right? So they are very powerful. They have very large field of view, very discretized and very robust. So the idea is to try to emulate that and then see whether we could do something like that. So certainly interesting area actually, right? So this is a since we are at it, so you can see here, right? This is actually what somebody is holding is a thin glass substrate, okay? And the circles that you see, they are lenses. They are meta lenses, and then you can see the focus point. You see, so the light is being focused by a thin flat lens. The lenses that we know, today they are bulk, right? Thick lenses. So you can see here about 45 lenses here on a thin substrate, and then you can do these kind of things. So the idea is, how do you miniaturize this and probably fit it into your camera? So the idea is to put this in cell phones to have wide coverage, right? The optics will be very, very thin. So right now, the problem in getting wide angle and resolution is the lens. The lens becomes thicker and very expensive, right? And that's why people with this, interesting hobby, they carry this, bazooka type lenses, right, with DSLR. Then this guy is serious about photography. And I don't know whether the pictures are good or not, but at least that shows his commitment that he wants to make good pictures. So the whole idea of that lens is to create that wavefront, right? Now the question is, can we thin it down, right? Why do you need such a huge focal length? Can we reduce the focal length and make thin lenses, right? This is all substrate lenses which called meta surface, and create compact images and so on. Could we have assignment solution? Oh, that's I've done. Yes. What is the next step? I'm really glad that we want to continue our journey. I'm really amazed, and thanks for asking that. There are different things I'm thinking about. Creating short courses, right, on specific topics. Somebody was asking about nanophotonics, or even these kind of meta surfaces, and very focused topics on modulators, let's say on fabrication or application wise. I'm trying to create something of that sort. I also need to find time to create those lectures, right? So that is something that I would like to do. But the PRISM program is going to actually create some new avenues for people who are really enthusiastic about photonic circuits. And as you have already mentioned, this whole pandemic is really playing out, against us. But right now we are preparing the program so that we can at least initiate some of these engagements online, and then see how we could take it forward. All right. So I would see there are plans for us to get engaged. Keep your eyes and ears open. You will hear from us. Okay. Parallel processing using metasurfaces. Probably, yeah, you can do a lot of interesting things. Pick material for exam. I don't know what that means. You just follow through your what do you call the assignments, right? So when you go through your assignments, that should be good enough, right? That's fine. Yeah, Manish has an interesting question on integration of lasers on PIC. It's challenging. So, he has made a statement and then put a question mark at the end, right? So it is challenging, right? But it is not, something that we can't do. People have demonstrated laser integration on chip. There are two different ways of doing that. People have done them. It's all about, whether you want to do it or not, right? So how much interest or motivation we have to do this for a certain application, for example. For a good example is transceivers, right? For in the communication band, integrating a laser makes sense, right? But it doesn't make sense to put a laser when you're doing a sensing, right? So when you're doing sensing, you want the photonic circuit that will do the sensing, and then you want to discard this chip, right? So it should be discarded because you have already used it, right? You can do fluidics and so on to reuse that, but you don't want to add too much of overhead, right? Invest too much of investment on a single chip. In some cases, it makes sense to integrate lasers, and people have done that. It is challenging, but it is doable. There are different routes to do that. But there are situations where you don't want to integrate lasers or even photodetectors on chip. This integration will add additional process steps and overheads, right? When I say overheads, it adds cost to this. You don't want to do that. So in those scenarios, it's better to avoid that. So that's my view on that. It is challenging yet doable. Another question from Nikhil. So what is the minimum detectable power? Picowatts of photodetector at 1550 for nanosecond. It's doable. It's doable. It's all about working with the noise, right? So picowatts of power is quite a lot, right? So picowatts of power one can easily detect using a photodetector, right? Particularly in a guided wave system, you can certainly do that. And 5 nanoseconds is a long enough time that you should be able to integrate and measure it. It's oh, it's an assignment. Okay, wait for the solutions. We'll post the solutions, you can have a look at it. All right, good. As always, we had very good discussion. Yes, Nikhil.
Sir,
No, sorry, Akhil.
how in pace matching condition, how refractive index can be managed, sir?
So the problem with using refractive index to phase match is dynamic in nature. So if you want to change the refractive index to phase match, then you have to have some mechanism, like I mentioned, thermo-optic or electro-optic. A better way to phase match is taking help of physical geometry, right? You can increase the width or height, or when you're using a directional coupler, you can change the lateral dimension, the width, the height, and also the gap between the two optical waveguides. So these are all the ways one can change in order to achieve phase matching. If you are looking at Using refractive index change to achieve phase matching, you need to have external energy to do that. For example, electro-optic or magneto-optic or thermo-optic, where the refractive index of the material will change, right? So physically the dimensions are identical, and you can change the refractive index so that you can have this phase matching. And that tunability is also reasonably limited because you cannot increase the temperature, too much, right? And the electric field cannot be, applied infinitely large. You also have the response from the material, right? So the material response also plays a role. So changing the dimension is a better way to do that. Single photon detector at room temperature. Well, we are working on it. So there is a team here at IAC where we are trying to actually generate single photons and detect single photons on chip. The single photon detector on chip is something that we are all excited about. But single photon detector detection at room temperature, main problem is the noise. Okay, so the reason why we are going down low in the temperature scale is to reduce the thermal noise that we have, right? So till date, I don't think we have a room temperature, a single photon detection, right? Yet, but there are hopes of doing this detection, using, for example, room temperature superconductors, right? So there is a way to do that. So there is an interest in moving in that direction. But at this point of time, we are primarily limited by the noise at room temperature. So right now we don't have. Okay. So photonic microprocessors we don't have. However, there are efforts to integrate photonics in the microprocessors. As you know, Jihan was asking earlier that whether we can, where to use photonic ICs and so on. Right now, there is a project that IBM is pushing for, and Intel both are in the race to integrate, photonics with microprocessors. It will take a while for us to see it, but today we don't have. But there are flavors of electronics and photonics integrated systems. So you have photonic IC and electronics in a single system, but they are not doing processing for the moment. Okay, so what are tunable laser? Does it mean we can change the frequency of laser by few orders? If I'm thinking right now, how can we achieve this once a semiconductor laser fabricated? Okay, so tunable lasers, right? So what do we mean by tunable laser? Tunable lasers means you have a laser, single frequency laser, right? Whether I can change my center frequency or the wavelength, right? So this is called tunable laser. Okay, just give me a second. I will close the door. Okay, the wind has opened my door. So this is what the tunable laser means. So you have a laser generating a certain frequency. Whether the frequency can be tuned, right? Or the wavelength can be tuned, and this is what we call tunable laser. All lasers by design are tunable, right? Inherently, right? Not even by design. I would say inherently lasers are tunable. The question is the range of tunability, right? So when I change the current, you can have a look at the nodes, right? When you change the current, right, you can also change the center frequency. Okay, when you change the temperature, you can change the right? So these changes are very subtle, right? Very small changes, a nanometer to, in some cases, not beyond that. But then we do have tunable laser. There is a tunable laser in our lab that can tune for 100 nanometers. That's massive, right? So how do we do that? And that is taken care by the design. So you have a gain medium, and then you have the cavity. I change the cavity, right? The longitudinal modes, you have transverse modes and then longitudinal modes, right? So the top, when I change the longitudinal mode there, I can generate new wavelengths or take out new wavelengths, okay? So that is the tunable laser that we all see, because if you find any tunable laser, you will see when you change the frequency, there will be a motor inside actually moving. Okay, so what it is actually doing is changing the cavity. Okay, so that is how the tunable lasers work. And particularly, the question here is, can we do it on chip? The question is yes. So I can have a waveguide, and then I can have an active laser or a gain medium put on the chip, right? And then I can have mirrors, right? So I can tune the cavity either using thermo-optic, right? I don't have to move. I can apply thermo-optic tuning that will allow me to move the laser. So this is something that you can also do when you have laser integrated photonic ICs. And semiconductor lasers, if you have already fabricated, the facets are all nicely done. Tuning that is going to be hard. The only tuning that you can do is temperature dependent tuning, current tuning. So the tuning range will be limited. You can't tune hundreds of nanometers unless you put it into a cavity. So then you have an amplifying medium and an external cavity. Biophotonic structures like bioluminescence. At this point of time, not so much. Interestingly, I don't know, this is coincidence that I get questions about meta surface that I was reading, and this about biophotonics. Today morning, we had a discussion with somebody in Agarkar Institute in Pune. They do research in diatoms, right? So I don't know how whether you heard of this term called diatoms, right? So diatoms are organic living things, but they are formed by silica, right? So they are sand, they are glass, right? SiO2, right? Silica, but they are protected by silica, but they have life form inside. So they are microorganisms, right? And these organisms, they are very nicely patterned. Okay, so those patterns tell us something about very interesting optical properties of these diatoms. Okay, and also looking at things like butterflies, right, and dragonflies and so on, that has intrinsic nature to do that. And this fireflies is something that interesting that somebody has mentioned. But in my group, we have not done much on that. We are thinking of starting something in that direction, because it looks very interesting to look at the nature and then try to understand from it. But biosensing or biophotonic sensing is something that we do, but not really biophotonics. And it's coming up. We'll see how it evolves. It's not easy to understand nature, so we are trying to. Right. Yeah, deep. Yeah. So those are interesting things there. Okay. Yeah. So this is the last live session. So somebody else we have one more. Unfortunately, no. So we are at the end of this live session. Actually, we had more than 1 hour of discussion. So thank you everyone for tuning in and keeping this discussion live. So thank you very much for all your contributions.
Sir, where are you from?
Thank you
Right
so
now
much, sir.
I'm in Bangalore.
Okay.
I'm originally from Madras. I was born and brought up in Madras, but I moved around places, not in India, so outside. But I'm now, settled here in Bangalore. In particular, IISc. I live on campus, so my house is, probably about 600 meters from here. All right, good. Thank you very much, Jihan. I'm glad that you guys found it useful, right? Thank you everyone for attending, right? Best wishes. No need to worry for the exam. Just, make sure that you go through all the assignments, notes properly. It should not be a problem. Okay, don't get. It's not the usual exam types. Okay. Best wishes. I hope we will meet each other sometime, right? Glad that you guys are interested in the course. Take care, stay safe, and have a great evening. Thank you very much.
Thank you, sir.
Thank you so much, sir, and rest of my fellow mates.
Thank you. Thank you.
Yes,
Naveen,
sir.
we can close.
Yes, sir. We'll